In this lesson we're going to introduce and explore the exponential function, which features the number e. But before we get to that, I just want to review the number system that we work with and see where e fits into this. So our number system can be divided into real numbers and complex numbers, and you may have seen what we call imaginary numbers, which deal with I, and that enables us to do things like square root negative numbers. E is not a complex number, E is a real number, and the real numbers can be split into rational and irrational. Rational numbers can always be written as a fraction with integer numerator and denominator, so A over B. For example, 0.75 is rational because it can be written as 3/4. Whole numbers can always be rational because they can be written as over 1. And any recurring decimal, such as 0.3 recurring, is rational. Irrational numbers cannot be written as a fraction. For example, √2 and pi, which you've already met, and e is an irrational number. If we were to write it as a decimal, it would be an infinitely non-recurring decimal. Now e is defined as the limit, as n tends to infinity, of 1 plus 1 over n to the power of n. And as a decimal, it's approximately equal to 2.71828. Now, exponential expressions are those where the variable is in the index of the expression. For example, 2 to the power of x or 3 to the power of n minus 1. And we're particularly interested in those expressions where the base is e. So check on your calculator. Your calculator should have an e to the x button, or it might look like an e with a template box. Check on your calculator that e to the power of 1 is indeed 2.71828, and then also check to make sure that you're getting these values for e squared and e to the power of negative 0.5. Amazingly, this number e can be used to help us describe mathematically many real-life situations involving growth and decay, such as population growth or radioactive decay. Growth and decay can be described using a formula like this, where A is the amount of the population or radioactive material at a particular time t. A0 is the initial amount, so when t equals 0, and k is some constant which will depend on the particular situation being described. So I'll work through a couple of examples, but ideally you should pause the video now and try them for yourself before watching my solution. Here we have a culture of bacteria growing according to this rule. So n is the number of bacteria. We need to determine the number of bacteria present, firstly when observation commences, so that's when t equals 0. And if we substitute t equals 0 into this formula, we have n approximately equal to 2000 e to the 0.75 times 0. Now, of course, that is 2000 e to the 0, but e to the 0 is 1, so we have 2000 bacteria. Now remember the formula from before, that's our A0, because when t is 0 at the beginning, the initial amount, this e to the kt will equal 1, and that's why A0 is our initial amount. Secondly, 3 days after observation commenced, we have approximately 18,975 bacteria, and 10 days after observation commenced, 3,616,085. But when we're estimating in situations like this, 2 significant figures is usually sufficient, so we'll round each of these to 2 significant figures. So that's 19,000 bacteria approximately 3 days after observation commenced, and 3.6 million 10 days after observation commenced. In this second example, we're investing $1,000 at 12% interest, and we're told that we're compounding continuously, which is the clue here that this function is going to involve e. Now, to work out the amount after t years, we know that 1,000 is our initial investment, and then it's 12% per annum interest, so 0.12 t, where t is the time in years. Now this time we're looking for the value of t when the investment reaches $8,000. So we're looking for how many years it's going to take for that $1,000 to be worth $8,000. So we substitute in 8,000 for A, and if you have a CAS calculator you can solve this using the solve function. So t is 17.3 years, rounded to 1 decimal place. If the question was phrased slightly differently, if it was saying after how many years would the value be worth at least $8,000, we would need to round t up to 18, because after 17 years we wouldn't quite have 8,000. So you do need to read the question carefully. This one's asking us for 1 decimal place, the 17.3 is fine.